Welcome to today's webinar, Design of Point-Supported Glass Panes and Insulating Glass Panes in RFEM. My name is Moritz Bertram. I will lead you through the presentation. Meanwhile, my colleague Ulrich Lex will answer your questions. He is responsible for our glass module that I will introduce to you today. We will model and calculate a glass canopy and an insulating glass pane. You see the glass canopy on the right side of the screen. You can ask questions using the control panel, which is usually located on the right side of your screen. You can show and hide it using this button. You can use this field to ask questions, and if you need to, you can adjust your audio device up here. Regarding the agenda, at first I will introduce to you some features of the add-on module RF Glass. Then we will go into the design of a point-supported glass canopy in RF Glass and the design of an insulating glass pane in RF Glass. Now we get to the main features of RF Glass. We can design toughened or laminated safety glass and insulating glass. We can do a design of curved glass, which we will not do today, but it's possible. We can consider some additional options. We can take into account the influence of a substructure. We can consider shear coupling between the layers, and we can take climatic loads into account, which we will do in the second example today. And of course we can do all kinds of ultimate and serviceability limit state designs. Let's have a quick look onto our first example, the glass canopy. This is the complete construction that we are going to model today. However, we will not model the point supports themselves. Ulrich Lex has done this for our knowledge base some time ago, and you can find that on our website. Oh, this is still in German. Let's go to English. Over support and learning and the knowledge base in the upper left corner, you get to the knowledge base. Here you can do a full text search or search for all kinds of categories. In this case, I will search for point supported, which brings me to some technical articles. Two of these are for RF Glass and written by Ulrich Lex. The first one is using a simplified method, and the second, which we will use today, is using the FE analysis. The utilization is a little lower here than using the simplified method, which is due to the more exact FE method. This article shows the exact discretization of the point supports. For a model, we will use the model file number 4 down here, which contains a verified point support using a general technical approval from the company Glassline. I will show you later on. Now, the technical article consists of roughly 3 steps. The first step is doing the discretization in the bore area according to DIN 18008 NXB. Here, the standard defines a specific model with a given load and an accurately defined borehole, and the FE mesh has to be refined. You see that here. Until the internal forces are within a certain range between 46 and 52 newtons per square millimeter. We get to 48.2 millimeters, which is well within this range. The second step is modeling the support and the verification of the support stiffness. According to this general technical approval I mentioned before. So the point support is consisting of this bolt in the middle, two rigid surfaces on the top and on the bottom, and the glass pane in the middle, and two contact solids or contact solids between these surfaces, transferring pressure and failing under tension. From defined loading and a deformation, a spring constant can be calculated. Let's have a quick look at the technical approval. Here you see this point support. On top and on the bottom we have these rigid surfaces, the bolt in the middle. These black areas are our contact solids, and the glass panes on the left and on the right. And in this next step you see the formula, the equation for the spring constants with a range of values from 28 newtons per millimeter to 42 newtons per millimeter, and over using an adjustment of the E and G module of the contact solid, we can get within this range. I go back to the PowerPoint and to the next step. The third step is a complete model combining the first and the second step in one model with one point support and the FE mesh refinement, so we get specified deformations and and support forces for the verification of the model. Going back to the technical approval, we have this model on the top left. It's actually quarter of a construction, but since it's symmetric in both directions, we can use this simplification. On the bottom you see the results we have to expect. In this case it would be a deformation of between 3.6 and 3.9 millimeters and some specified support forces. And if we go into this specific model, it's this one, it's already calculated, and we have a deformation of a maximum of 3.8 millimeters. You might remember that we have to be between 3.6 and 3.9, so that's okay. And the support forces are okay as well, so we can use this as a verification of this point support. Now let's go back to this complete model of the canopy. According to the standard, we have to meet certain requirements for the point supports. We have to have at least 3 point supports. We have 4 in this case. The diameter of the point supports has to be at least 50 millimeters. We have 52. The distance of the point support or of the center of the point support to the edge of the pane has to be between 80 and 300 millimeters. We are at 250 millimeters, so that's okay. And we have to have laminated safety glass with a thickness of 2 × 6 millimeters with an intermediate foil of from PVB with a minimum of 1.52 millimeters. We will define that later on. So I make a new model, call it canopy. We will classify our loads and combinations according to the German standard DIN 1055-100 and the DIN 18008 for glass, and create our combinations automatically. So now we have a new empty model and can start making the model. I have to adjust my grid from 1 by 1 meter to 0.1 by 0.1 meter to make life easier for me. And I want to look from the top on this grid. Now I will adjust my FE-mesh settings right at first and want to have an FE-mesh target length of 0.025 meters, 25 millimeters, and can start modeling right away with a new rectangular surface. We can omit the material and the thickness for now, since this is later on defined in the glass module. So we go over that, click OK, and make our glass pane 1.4 by 1.1 meter big. Now we want to copy this bottom left node by 25 meters in 25 centimeters in each direction into the surface. This is the location of our point support later on. We want to copy that point support from this model file from the article. I go into view into Z direction, select everything I want to copy, deselect the support since I want to work with a substructure, and now I can just hit Ctrl+C on my keyboard, change to my new file, and via Ctrl+V I can enter this point support into the structure. I'll quickly change into the wireframe model since it makes it easier to move this point support around. Select everything belonging to the point support, including the FE-mesh refinement, and move that without any copy with the displacement vector from the center of the support to my node. Click OK, and now I've moved this to the right place. The next I will do is modeling my substructure. For that I copy my center node by 10 centimeters into Z direction, 0.1 meter, one copy. Okay, there's the node, and I want to make a new beam between the bottom of the bolt to my new node. it's around 20. Okay. From the bottom of the bolt to the node. Because I want to have that in all 4 corners. I select that whole support and copy it by minus 70 centimeters into Y direction. Okay. I'm going back to my solid transparent model, so I have a better understanding of what I'm doing. And I will copy some more points for my substructure. Copy that one again. And once more. So I have everything, all the nodes I need, and I want to make a new member. In this case, it's supposed to be a pipe cross-section. I go to the library and select this pipe according to the German standard DIN EN 10-220, and I want to use a 48.3 by 2 from this to this, and I want to have an additional strut with a cross section around 20, not around 16. Okay. And now I'm pretty much done with the first part of my substructure and need some nodal supports. I have to define that with supports in X, Y, and Z direction and a restraint around globally Y. Forgot that one. Okay. So I got that for these two wall attachments. And I turn that around so I can copy this whole part of the structure by 90 centimeters into X direction. So we're pretty much done. Although the construction has to be modeled with an inclination of 5 degrees from the outer wall of the building, which is on this side, because water has to run down, snow has to fall down, so it's not supposed to be straight. We could rotate everything around 1 point, which would be okay, but this would result in other points being shifted sideways, which we don't want. So we have the function chamfer, or select everything, right-click on the structure and select this option, chamfer. With an angle of 5 degrees about the x-axis in direction Z, and the starting plane, some point in the starting plane is, for example, one of my supports. I click OK, and this whole structure has been chamfered. Okay, So the structure is done. We have to have some loads. For that, I define a new load case, self-weight, which is a permanent action. The self-weight of the structure is considered by the program if I have this check turned on with a factor of 1 into z direction. The next load case will be snow. So we got all our load cases done. I can go through this dialog, do the combination right away. So we've done everything we need. These combination expressions for the ultimate limit state and the 3 options for the serviceability limit state are chosen by default, and I will just leave them like that. So I click OK, and I have to add some load for the snow load case. I use a new surface load. It's supposed to be a uniform force globally related to the projected area with a magnitude of 1.3 kilonewtons per square meter. Okay, set that on my surface, and now you see we have some little gaps in the area of the point supports. We want to fix that and put the line loads on the outline of the openings on this structure, and we can do that using tools, generate loads, and from area loads on openings. The area load direction is again ZP, magnitude is 1.3 again, and I have to select the openings. So I select them. Oh, they've already been selected before, so I deselect them and select them again. Openings 2 through 5. Okay. 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 And now you see the generated loads from the area loads on the openings. So we got the loading on the whole surface now and are done with the modeling itself, and we go into the module RF glass. Here all the surfaces that are consisting of glass have been selected automatically. Our main surface still consists of concrete, so it's not taken into account yet, but I can just go ahead and select it, click OK, so it's in there now. For the ultimate limit state, I select the combinations 1 and 2, and for the serviceability limit state, I use combinations 3 through 7. We want to do a global calculation now, since if we do the local calculation, we have to define line supports and nodal supports and boundary members and everything we have. Inside the module, we are going to do that in the second example. For the first, we use the global calculation because we want to take our substructure into account. The standard is the DIN 18008, although you also have the option to do a calculation without any standard. It's just a stress design then. I go on to the layers. I have to select all of my surfaces now. all of my glass surfaces. So I go use the pick function. No, didn't want that. I go back to the general data, select my surfaces there since they've already been selected, and copy them into this field. Now I make my layers of the glass pane. First layer is glass of heat strengthened float glass with a thickness of 8 millimeters. Remember, we have to have at least 6. Then a foil from PVB with a thickness of 1.52, as is has to be done according to the standard. And the third layer is glass again the one we did up here, used up there. 2 times 8 is bigger than 2 times 6, so that's okay. And both are supposed to be laminated safety glass. We have a quick look into our composition details. According to the standard, we must not consider coupling between the layers. So I turn that off, although it might be possible that the internal forces are bigger with coupling, so the calculation might have to be done twice, but I turn off the coupling now. Okay. We have a quick look at the details. Here you can select all the stresses you want to display. You can select the bending, plate bending theory and the calculation of the equivalent stresses. And you can select which results are supposed to be displayed. Okay. Then we go on to the load duration. Everything's okay here, so we don't need to take any more or put any more attention to that. And we go to the serviceability data. Here we want to do a serviceability design for our main glass pane. Since it's deformation, this is going to be the governing one. The standard or the default reference length is the minimum boundary line. We want to have the distance between our supports, so we go to we use it user defined and select the distance between our supports, 0.9 meters. Now we could start the calculation. This would take a while due to the nonlinearities and the contact solids, and would be too much for the webinar. So I've done that before and can go into the complete model with results. I go back to the module RF glass. Here I can see I have a maximum design ratio, stress ratio of 89%. And if I filter that for the maximum, I can see it's at combination 2 at the top side of the surface, actually of both surfaces, since we don't have the coupling activated. And I can also have a look where this maximum stress happens. It's directly at the point support. Now I go back and have a look at the maximum displacements. In this case it's 3.2 millimeters, which is okay. 9 would be possible, and the ratio is 36%. So we're totally okay with that. So what can we do now? We can, for example, no, we can go back. I want the stress ratio, and I want to print that into my where was I? This one, 32. I was at 89%, so it's combination 2. Yeah, exactly. 89%. I want to print that into my printout report. Maybe viewing it in the wireframe display model. And we see the maximum is somewhere in here. Now I can print the graphic, print it to the printout report as a screen view. So I make a new printout report. In this printout report, you get all the input data, all the results for the RFEM calculation, and also all the input data and results for the RF glass calculation. Also, you can just edit that by using additional pictures, turning off and on tables as you wish. It's up to you what you want to print. So this design is actually pretty easy. Of course, we have used the previously prepared point support, which takes a bit of time we don't have in the webinar. And if you have a different point fastener, you have to do the verification according to the technical approval, as Ulrich Lex did for our model. So we're done with the canopy and move on to our other model, our second example, the insulating glass pane. So I make a new model, call that insulating glass pane. We do the classification according to the same standard again and create the combinations automatically. Now we go into the XZ work plane, and since we don't have an even size like before, we can just define our glass pane using node coordinates. We start at 0, 0, 0, and the opposite corner is 88.5 centimeters by 138.5 meter, 1.385 meters. Okay, now we want that at minus, so it looks nicer. And we make a new rectangular surface. Again, thickness and material don't matter now. And we have defined our surface. The next, what we do is the loading again. The First load case is of course self-weight with the activated self-weight. Second load case is wind. The third load case is the difference in the altitude. This is a permanent load. Our fourth load case is the atmospheric pressure. This is actually a temperature load. And our fifth load case is the temperature difference which is a temperature load case as well. Okay, we go back to load case. The whole combination is done automatically in the background. We go back to the wind load case and defined a new surface load with a magnitude of 0.5 kilonewtons per square meter in local z direction. Put that on the surface and we are done with our input in RFEM. Everything else is defined in RF class. So we go into the module. All surfaces are supposed to be designed. It's just one. The standard is the DIN 18008 again. Now the calculation type is supposed to be local, so we have to enter our supports. For the ultimate limit state, we use the combinations 1 through 11, and for the serviceability limit state, we use combinations 12 through 28. From here we go on to the layers again. In this case, we want the first layer to be glass again, heat strength and float glass as before, with a thickness of just 4 millimeters, and it's supposed to be thermally toughened. The second layer is gas, it's just dry air, with a thickness of 12 millimeters. Third layer is glass again, in this case float glass with a thickness of 3 millimeters. Then we have another layer of air, and the last layer is heat strengthened float glass again, with a thickness of 4 millimeters. Surface has to be selected. And now we need to go into the composition details again. In the last model, we adjusted our FE mesh length through RFEM. We can also do it here, at least for the local calculation. We activate the FE mesh refinement and have a target FE length of 0.05 meters, 5 centimeters. That is sufficient. And we're done with that. The next is the line supports. We want to have a perpendicular a support perpendicular to the surface on all lines, and we use the hinged type 3 for that. This is referring to the reference to the local reference system. If we have a user-defined support type, we can also use the global reference system. But we stick to the hinged type 3 and are done with that with the line supports, and move on to the nodal supports. Here we want to have two nodal supports, so this doesn't move around. One in the coordinate origin at node number 1. This support is supposed to be a user-defined support with restraint and with support in X direction and Z direction, so it can't move into X direction and can't fall down. Can still rotate around that, so we have to have another nodal support on node number 3. And here we want to use the hinged type 3. So this can move in all directions but the Z direction, and is a pin support, so we don't have any restraints in our glass pane, which is important. Now we can move on to the boundary members. We don't have any boundary members in this example, but you can use it, for example, for the consideration of handrails. Then we go to window 1.6, climatic load parameters for insulating glass. We leave all the values as they are for summer and winter because they comply with the standard. The only thing we have to do is select the load cases for the climatic loads. I could also just define them in this window, but we have already done that, so we can just select them. We also have to do that for the winter, temperature differences, atmospheric pressure differences, and altitude difference. Okay, then we can go on to the insulating glass unit. Here I can, for example, consider a secondary seal for the stiffness of a secondary seal if necessary. We just leave the default values. Also, the load distribution between the external and the internal loads can be adjusted just for additional loads that are defined directly in RFEM. For example, we could do that for the wind load here and apply 50% on the inside, 50% on the outside. But we just leave it here for the self-weight and the climatic loads. The distribution happens automatically, so we can leave the default settings. We go on to the load duration. Here we have to adjust the atmospheric pressure, which is a medium-term duration, as well as the temperature difference, which is medium-term too. And the last window is the serviceability data again. We have to add our surface, and in this case the reference length for the minimum boundary line is what we want to use. So we are done with the input in RFEM and RFGlass. The calculation would take a few minutes again, so I switch to the complete insulating glass pane that has already been calculated. I go into the module, and now I see that the maximum stress ratio is at 26%, so this is still a good value. We could even go a little smaller on the sizes, I think. And I can look for the maximum stresses in this model. It's at combination 3 and 4 in the summer with a value of 12.03 newtons per square millimeter at the limit of 46.67. And you see it's on the layer number 5 on the outside of the glass pane. We can do the same for the displacements again. The maximum is a displacement of 4.6 millimeters at a limit of 8.8 millimeters, so we are at a ratio of 52%, which is okay. And when I close the module, I can have a closer look at the at my results, at the utilization. For example, the ratio, you see, oh, this looks a little funny. But that's what it's supposed to be. Okay, I can print everything to the print auto report again and make it clean. So that's it for the presentation. You've seen the two different approaches for the calculation using the global and the local design for glass panes in RFEM. If you have any questions or need help, just drop us an email. We'll be glad to help you with your problems. If you don't have our programs yet, feel free to download a trial version from our website. With these versions, you can test our programs completely without any restrictions for 90 days. I thank you for your attention, and I thank Ulrich Lex for answering your questions. If you didn't get an answer yet, we will follow up on that in the next couple of days. Have a nice afternoon. Goodbye.